So today we're going to look at the one of the best RNN hack tutorial / blog post I have ever found. I even don't remember how I found it, but this guy Danijar, I'm not sure if I spelled it correctly. He even have the BibTeX citation, so he wants himself to be cited. Actually, you can do a quick check if you can cite him. So if let's go to the semantic scholar. Let's see if because this is so good, and let's see if somebody is citing it. Also, so in the PyTorch blog, not the PyTorch blog, but in PyTorch forum, that they are recommending to implement some of those as defaults. Okay, probably we'll need to look for that reference specifically. It was not so easy to find it. Anyway, I would not be surprised if the people are referencing to this. So the idea is that he gives some of the tricks to improve the performance of the LSTMs and also the references, basically any recurrent neural networks references, how to improve that. So one of the things is so we can go step by step. Some of them we will not implement right now, but in general, all of them are quite good. So the source code is available on the left side, by the way. So the one is that they recommend to use the adaptive learning rate, and so you already know about them. So this is, I think, just one comment regarding this, because many state-of-the-art models use these learning rate schedulers that actually are not really friendly with the adaptive learning rate optimizers, because you can imagine the poor guy adaptive optimizer wants to estimate the gradient acceleration in some parts of the learning space, and then if you have the scheduler, you troll him off all the time. So anyways, so the rule of thumb in general would not be to use ADAM or these adaptive cool optimizers together with the learning rate schedulers. The learning rate schedulers work good with the simple SGD with momentum, but at the same time, from my experience, always much better to use adaptive learning rate rather than those schedulers. So if somebody have different experience, you can share that. That'd be interesting. But my experience is that. Then the gradient clipping, that is often used in reinforcement learning. So you can easily clip as the max value of the gradient at any stage of your function graph. But we're not going to use that now. Then normalizing the loss to get losses similar magnitude across datasets. Divide them by the maximum sequence length. Oh, this is quite a fun thing I did not notice before. So to get losses similar magnitude like your datasets, so if you have different sequence lengths, he advised to divide the loss by the maximum sequence length, I guess of the batch probably. So that sounds quite cool idea. Then truncated backpropagation. That's something that is already by default. Recurrent neural networks can have a hard time noisy gradients, vanishing gradients, right? Okay, yeah, so this is also a cool idea. So because the long sequences, you can have vanishing gradients for the some of the RNN models. Like last time we looked at phased LSTM that don't have this problem. But in general, the one way how to reduce this problem is by using overlapping sequences, like with some kind of step. Then long training time, this is also fun. Some of the LSTMs converge after longer time period, like when you have the loss not actually changing much, but the accuracy and quality still improves. So then multi-step loss. Okay, so this is a little bit tricky when you have the teacher and the learner, so two models. This we're not going to use, but now we're starting to do some things that we're going to do today. So about the network structure. So one is to use Gairu. We will not do that today, but the Gairu is a little bit smaller like cell, so it would be very easy to convert what we're going to do today to GRU units. Then the other thing is layer normalization. So this is something that the fun thing, I think, that layer norm, when this is like a layer norm is basically the same as group norm. It's just that the group is one. If you look at the paper, I think those guys actually mentioned in their own paper that this is used with LSTM. So when they invented layer norm, I think the layer norm was in general invented before the group norm, and the instant, like I'm not sure, like the order 2016. They specifically say that if you add layer norm to all linear projections in LSTM, you get quite cool results. Basically, you can see that, for example, here on some of the steps, the convergence is like so much better with these layer norms, and also there was a lot of tasks where they show that the accuracy and everything is much better if you just add layer norms for all of the linear normalizations, linear projections inside the LSTM or Gairu, doesn't matter. So let's do that. From my experience, when we tested all of these things with our models of different kind of problems, the layer norm was a huge impact. So you can get, I think, like in some hard datasets, we got 3 to 5% improvement just by adding the layer norms. And if you read again in the PyTorch forums, they discuss, and I think if I remember correctly, they even have it already. So the layer norm LSTM PyTorch, that they have already implemented it, if I remember correctly, inside the official branch at somewhere. So custom LSTM benchmarks. Okay, I was not able to find it quickly, but if I remember correctly, they had it. Oh, there are some interesting LSTM variants. So anyways, so this is what you need to do anyway. So let's do that in the code. I will go to the code. So you can type in chat as well if you want to ask something, or you can also try to jump in the conversation. So let's see. So I added also some to-dos somewhere. Let's try to find. Did I add to-dos or not? Okay, I did not add to-dos. Okay, so we can do that anyways. So the model. So we have multi-layer LSTM here, and we have the cell here. Actually, this is a phased LSTM cell. Phased LSTM cell, but it's not actually phased LSTM. Sorry for that. I remember that it was not phased. Yeah. So let's rename this. So rename this to SOTA LSTM, state-of-the-art LSTM. So I just used the PyCharm rename function. I also will not need this function. So it actually doesn't matter. You can leave it as it is, but I forgot to change the name there. That's why I wanted to fix it. So we'll need to add the layer norms for all of the linear projections to make this exactly right as it was in the paper. We should have the layer norms for for every linear projection separately, but as you know, some of them are tied together with that equation where you try to project linear projection directly on all of the gates at once, So there is this first part of the projection and then the second part. So in a classic implementation, you even have just one part because you don't have peepholes. So in this presentation, we also have peepholes. That's why we have two these projections. So you can actually have, if you have a simple LSTM, you can have just one projection with all of the gates at once, because there is no peepholes, and then basically you could have the layer norm for each of the sections of that. But in my case, I just don't want to change that too much. So let me look at that. So I had so one option is just to write it down now. Just a second. So I'm not sure, maybe I accidentally shared with you some wrong code. Okay, I think, but okay, no, that's fine. So I'm just checking with my own code that I did before. Just a second. So if I will not be able to find it, then we'll have to do it from scratch. Funny. Oh, just a second. I thought I did it, so if I will not find my own notes, then I will just code it live, and then probably I will have some bugs, but just give me a second. That is funny that I somehow lost it. Okay, this is not expected, so let's do it live. So I somehow lost my notes, but still I can do this, I believe. So okay, so one is that we need those layer norms. So the layer norm, so this is going to be the layer norm 1. So we'll have two layer norms because we have two parts of these calculations, and so I don't want to split this in 3 parts, so that's why I will just use the group norm. So it will be similar idea, torch and n group norm, and the groups will be of course num groups will be 3 because we have 3 parts of that. So this is not specifically saying that they will form the correct layer norms, but in general the capability is the same basically. So here will be also with the group norm add the number of channels. The number of channels now, let me think, so we'll have the 3 groups, we'll have the number of channels. I believe it should be hidden size, but we'll see. So if I add the hidden size here, and let's test this also in the bottom part here, and then I will also pause so you can catch up. I will show you back this place. So there is the linear projection. So just after the linear projections, we want to add the layer norms to center them around this data space. So gates, forward, gates, and now let's check if there is no bugs. So just to check, okay. Yeah, so maybe at some point while you will catch up, I will look for my notes. That's funny how I lost them. So, okay, running, what is happening? I press run. Let me check data, project, data, there is a data. So the max length, Okay, so I will probably reduce the max length just to make sure that it's running and not something is not working, so that there is everything working. Okay, I'm running this on CPU, and on Google Colab we can run this on GPU. So I added.
So I got error from this.
Yeah.
The sizes. Yeah.
Okay. So yeah, I want to see my error. I'm not sure why it's not working. So just a second. What is happening? Not sure. Maybe I updated my code sometimes. Really not sure. Okay, I'm running the wrong code. Sorry. So I'm running the wrong code. Okay, I had to change this. Okay. So, and I also want to just make sure that I had not lost my notes, or did I lose them? Find the layer norm. Maybe I have them somewhere. So layer norm LSTM simple LSTM layer norm simple layer norm peepholes. Okay, interesting. Did not see those. Just a second. I will find my notes and then it will be much faster. So
Isn't there, because of group norm mostly is used for three-dimensional data, we have only two dimensions like batch and features?
should not be. Should not be the problem.
Because it kind of matches up. We have 3 times 64. It matches with the 192. So I don't know what's the problem.
Just a second. We can debug, of course, but let me check. It's definitely not what I expected. Doesn't matter. Okay. The group norm, number of channels. Okay. Number of channels, groups. Okay, division. Okay, I guess it cannot divide that probably. Okay. So let's back up. So let's use the layer norm. So this will not be exact implementation, but still it will be better than nothing. So the idea would be that we can use the separate layer norms for each of those. Well, maybe let's do that. Let's do that. Otherwise, it will be not fair. So let's use then the 4 layer norms. So this will be layer norm 1. This will be hidden size of the num. So there should be something. What is the parameter name? The parameter name is normalized shape. Normalized shape, but it doesn't matter. You can just have the hidden size here. So this will be for the first gate. Maybe you can even call them with the gate names. With the gate names, what were the gate names here? So there will be input gate, norm input for get gate. Then there will be the output gate, and then there will be the C gate or the cell update gate. So this is going to be then the C gate. So we have 4 layer norms, and these 4 layer norms then we can use. So maybe I will drop them in the chat, this part of the code, if by some reason somebody don't catch up with that. So I dropped that part in the chat. So now here we can split out them and use them. So the input, even we can, the easier way probably is not to split them, but just add before the sigmoid here. So just like add it like that. So it's funny that I lost my notes, and now it will be more improvisation. So here is the for get gate. Then there will be the output gate. But I guess you can do this with group norm as well, but it will be fine with this one. So these ones. Then we need the C gate, the cell state gate stuff here around this one. And maybe even better, I will share in the chat not the code snippets directly, but the screenshot, so it's a little bit easier to follow because the formatting then is not clear. So if we add it like this, I will also run it and check. I believe it should work, but maybe I'm wrong. So I'm trying to share this code. So I'm generating a link. So the link is ready in the chat, the link for that bottom part. Okay, so I'm trying to run it. Okay, now it works. So this works. So I shared the code also in the chat. And also let's a little bit scroll up and share also this part in the chat with the screenshot. So you have two screenshots. And when you're ready with the layer norms, then post plus sign in the chat. So like that. So are layer norms okay? Plus minus. If minus, you can ask also some question. Meanwhile, I will try to look for those nodes. So I hope you can catch up with this part of the code. Okay, I found the nodes. So I will also show you, that part here. So if you would like to have the group norm there for the whole layer, then my problem was that the norm channels was actually not the output channels per every this group, but actually the correct one was this one. So you should have 3 groups and then the hidden size times 3, and then it would work. So it would be it would be possible to divide this one by 3, and then it will be no error. So but this method with the 4 layer norms is much better. It's like more it's exactly like in that paper. So that's cool. So let's see how you're succeeding. I don't see any pluses. Maybe I was a little bit too fast. Yeah. Is anyone trying to do this, or should I go? Okay. So so the Walters is posting that he's done with this, and I will wait a little bit and then show the other parts. Okay. So I hope that using those links, at least you can catch up a little bit later, or yeah, if you have some questions or problems, you can also help. So I will share again the the blog post. So the next thing is the feed forward layers first. So pre-processing the input with feed-forward layers allows your model to project data into space that is easier for temporal dynamics. So that is also true. We tested that if you add the linear projection before the RNN, actually the funny thing is that I remember that when we looked at some of the transformer models, they also used some linear projections before the feeding in the attention mechanism. And so in this model, actually, I think we already have that. So let me check if we have that. So the idea is that here we have the input features by hidden size. So that means for every time step, we do the linear projection, feed forward before the LSTMs. So that is already implemented here. So this is really good also way to not to forget those projections before the RNN. Then the next fun thing that I think this was really cool is the stacked recurrent neural networks. This is, I think, really cool idea. So it's interesting that for this one they don't have the reference. I'm not sure like why there should be some paper about it. So recurrent neural networks need a quadratic number of weights in their layer size. It can be more efficient to stack multiple layers than having one big one. So it means that it's better to have smaller LSTMs with a hidden size, let's say 128 or 64 or something like that, than just having one large LSTM with hidden size of thousands. So that is one thing. And the other thing cool is sum the outputs of all layers instead of using just the last one, similar like resonant or densenet. So this line I think is really cool. So it's the idea that you can have the skip connections between the LSTM layers or any other recurrent model layers. So we can do that. Let's try to do that. So it's basically, I don't know how to say it, just like some kind of resonant type of LSTM, and it also works really well. So let's look at that. So we have the layers stacked here with the sequential. That's fine, and the change will be actually very small, I think. So let's see. So we have LSTM called here. LSTM called here. So let's see. We have Z1, Z0. Then we can have the Z1 layers. Also one small nuance. If I scroll in the top part, now we have num layers 1. Please set num layers to, let's say, at least 2. Maybe 3 or 4. So num layer should be more than 1, because otherwise it doesn't make sense, this idea. So num layers 1. Now Z1 in the forward pass of the model LSTM. Z1 all. So this is going to be the, well, not all, but let's say layers. So we have here, we will collect all of the hidden states in between the layers. So let's collect those hidden states. So for in range of LSTM layers, and we can access actually sequential model. We can access, oh sorry, not like that, but E. We can access sequential model by index, if I remember correctly. So Z1 layers, append the self LSTM, these will be the layers actually. And then if I add the index here, E, forward, and we need some kind of .z0, and we append those to the layers and then replace that by the last value. So Z0 is 1 layers the -1 last value. That's cool. So now after this one, you'll have options. Okay, we don't need this line as well. So the options are following. So we can either do the densenet or resonant type of actions. So one is we can concatenate them. Densenet would be concatenate, concat, or we can use the resnet approach of sum. Or we can do both if we want. So, or we can do attention as well. So attention, that is another option. You can just learn some kind of weights with softmax and add it here. So multiply it here. So what here we can do then? Let's do the resonant type of thing. So the easiest way for the resonant, that would be layer size independent, I think, would be to calculate the mean value. So it's actually interesting that we already calculate the mean over the temporal pooling, but we can calculate it again also here. So first we need to stack them. Torch stack. Let's stack those z's. Z1 layers over dimension of 1, because that is the feature. Not, yeah, let me think. So is it a feature? Batch sequence. So that is the sequence dimension. So let me check. I will debug this a little bit. So then Z1 torch mean. So we can calculate the mean value of all layers basically. And the division part is good because we can change the number of layers and reduce a little bit the impact of that. Or another option is we can use the sum here, and then we need some kind of normalization after that. Let's say layer norm. If we add the sum plus layer norm, it will work just as fine. Or we can use the mean. So there are a lot of options that you can use, but the idea is that you have skip connections. So I will add the breakpoints here and just double check if this is correct. I slowly scroll up, sorry for that. Trying to run it now and see, maybe the line 184, maybe that's not correct. I'm not totally sure about that. Hopefully you can select it out like that. So I'm running it. Takes quite a long time.
Another way to do
Okay.
this without the sequential, I'm mostly using with these cases Torch NN module list. You can use it as a list and for the modules, and you can iterate through the layers without indexes.
Oh, without indexes, that's nice. Yeah, that could work. That's really good there. Yeah, but it worked also like this. So, but yeah, Walters is right. That is maybe better option to use. And so here then we try to stack it. So I just want to double check about the actual dimension of what we want to stack. So the first one will be the layers basically. Okay, so and then we'll let me check. So 0 size will be 16. That is batch size, sequence features, and then if I stack it, the Z1 shape is 16. But yeah, that's cool. So we created a new dimension basically. We created a layer dimension. So okay, let's write it down. So here, oh man, okay, so here we created the this is actually batch layers, then the sequence, and then the features. So now we have again options what to do. We can sum the layers as in resonant and then add the layer norm, or we can use my approach of having the mean value. So, and then after the mean value, we will eliminate again this dimension. We will reduce it as a mean value of those all of those features with every sequence time step. So it will be like that. And then the next thing is, as you see here, so it's actually not the hidden size, but basically features, doesn't matter, is that we reduce every sample just to features with the next line. And this is this is a temporal pooling. So one thing that often is used here, you can add also attention to look at what exact time step you want to pay more attention. Just learn one weight matrices and then apply softmax and then multiply that. That's another option, but this will be the simplest one. So the simplest one, I think, works. So if I now just try to run it again, and then I will give you this snippet of the code. This is really neat, a very easy trick to improve the gradient flow. So, but the one thing that I think is quite important is that you don't just jump over to this Z0. If you just have the link over the LSTM at all, I think that would not be beneficial. Then it would start learning just the patterns, not the time sequences. So my advice would be not to jump over the first layer, but maybe even, as I say, this could be interesting research topic. How, like, at what point you should start jumping? You know, maybe first couple of layers you should not have the gradient skips, but then at let's say the last layers, maybe if you have this gradient skips, it will be beneficial. That's a small interesting research, I think. So, and also these pooling methods, they are also, I think, quite interesting. So if you, yeah, maybe I'm not sure, like if you are really interested in those pooling methods, maybe I can do a small workshop next time about the pooling methods, about the attention mechanisms. So let me know in the chat if you want to have attention mechanisms in RNNs. So, okay, I see that Walter's shared the module list code. That's cool. So I will share also my code about this part, right? So this is good. This is ready. So I shared the code of that. Yeah, maybe let's take a small pause. So I'm writing in the chat, is the what is it called, like RNN resonant style skips ready? Skips ready. By the way, the skips there are so many options what you can do. You can even have to have it pure resonant type of skip. You can have they could be, let's say, added here, I think, as well. So this is Z here. Maybe you can have something like this Z plus 0. So, oh man, I didn't want to do this. So Z plus Z0. So maybe you could do this as well. So there are a lot of options, but if you do this, I think you should have then layer norm after this one. So for somebody looking for small research, there you have it. Like I think you can do a lot of interesting things with these skips. So you can do even that. Okay, let's I see 2 pluses. That's great. Let's move back to the great blog post that I really like. So. Yeah, then the learned initial state. So this is really cool idea. So I bet all of you have thought about this, that when you have LSTMs, why do we need to initialize the first hidden state as zeros? Why wouldn't, like, why the zeros is always the best value, you know? So that is true. So maybe he's saying that we can learn the initial state from basically your training dataset, and then we can predict the best initial state with which we could start with any situation. That's, I think, is really cool idea. So it is referencing to this post. Let me quickly open that post. So non-zero initial states from 2016, some kind of small research. Okay, here's cool, interesting stuff. So the zero losses Then there is a noisy loss, so that this is initialized as noise, and then there is a noisy variable. So basically you initialize it as noisy and then learn it. So let's do that. That will be fun. So learnable initial state. I think that's really good there. So let's move back to the code. So we already know how to make things learnable, right? Because we already have a lot of parameters, right? So if you're following my tutorials, basically you already know that you can have parameter for everything. So we can easily make the learnable states. So let's do that. So the learnable states we can do by self h. So I think also the trick is that you need to initialize them noisy uniform probably. So h0, if you initialize them as zeros, probably it will not learn as good. And n parameter, and now there is a nasty thing. So the nasty thing is that in order for this to work properly, at least you can in inference you can probably like hack it, but you will need to have the same batch size because of course let me think actually the initial state. So it's not nasty thing actually. This is my mistake. You don't need batch size. I almost made a mistake. Because here is the batch size. We just need to extend it over the batch size because that's the same learnable state for every sample. So that's really cool. So self hidden state, hidden size, that will be good. Then we can make it noisy. We can make it noisy with the same deviation that before, I think. Uniform, hidden state, okay. So this will be h0 that we will extend over the batch size. So that I almost told a not good thing. So hc. So this is for hidden state, zero, and for the cell state. So we have two learnable parameters. And now we need to apply them. So we can apply them by, there are two methods, repeat or extend. The repeat, as I remember, was copying, extend is copying pointers. So let's see. So here h will be torch h extend. I hope, let me check if this is correct. Extend. Was it extend or some other function? Let me quickly double check it with the PyTorch documentation. Extend, because I now see the repeat and I can do this with repeat, but I think the extend was better. Was it extend? Tensor. Okay, let's see. If I will have mistake, then we'll fix it. So size by hidden size, and this is the same for C, and also to device. I almost forgot. Oh no, we don't need to have for device because it's already the parameter. So H and the C. So we're basically not. It's not reshaping. It's copying pointers. But I'm not sure about this extend. So let's see. If I add the breakpoint here and try to run it, if it will work or not. Or maybe I will just run the run. So if I remembered correctly, there was such a function, torch tensor expand, like okay, expand, sorry. I think it was expand next, not extend. Or yes, it was expand size.
From documentation you should use repeat,
because
no? Expand expand doesn't copy the data.
Yeah.
We should copy the data or no?
No, I don't need to copy the data.
Okay.
But but the funny thing is that does it really matter if it copies or not? Because for example, here I copied the data, but we can just replace it quickly with expand as well. I'm not sure. It should not affect the gradient, in my opinion. But if it does affect the gradient, then you should use expand. If somebody knows the answer, that would be interesting. So if I run it now, yeah, I believe both of those should not affect the gradient, but yeah, I think in most cases you could use expand. I just forgot about that function before. So if I run it, yeah, cool, it works. And even with this super small sample, also it doesn't matter actually. There is super small sample. So anyway, so it works. This is great. So we have learnable hidden and the cell state. And as you saw in that blog post and in that publication, that with this one you also get quite a big improvement. So I think you start sensing that if you just combine all of this stuff together with the phased LSTM before, I believe you can have super, like, really powerful model that could probably compete with the transformers. And I have seen actually some papers where they have all sorts of variations of LSTMs that can approach also the transformers, and transformers also have some disadvantages. So, okay, this is good. Let's see. So I posted the shared code also as a screenshot. So let's ask the question: is the Learnable H and C ready? Learnable H and C ready. Cool. We have 1+, so we're almost ready. Just a second. Yeah, just bear with me. I have a few things to show you more, and hopefully then you can make your own powerful models. So the forget gate. So this is a simple one and very effective. So especially when you have long sequences, if you initialize them by random, the forget gate. So if you remember, the forget gate will measure, like, it will have the sigmoid on top of it, and it will be multiplied by the hidden state, and will limit the amount of information coming from the previous time steps to the current time step. So if you have long sequence in the very beginning, it will be very disadvantageous if you have if you lose all of the information in the very beginning of the learning. And then later, basically the idea is that if we initialize the forget gates to ones, not to a uniform distribution, and the same idea is for GRU to reset gates to the -1, then we, in the beginning of the training, we will encourage to remember as much as information as possible, and then during the training, LSTM will start to forget some information that is not necessary. This is really a neat trick, very easy and very powerful. So we can do that. So I will go back to the code. Really like that blog post actually. So the initialization, let's see. So we need to find the forget gate. So let's see. So the forget gate is the dimension of here from multiplied by 2. So this is forget gate. So, and there is one other thing. I forgot, in the blog post it says need to initialize as ones the bias, because of course if we initialize the matrix as 1, then the dot product will make us like wonders. but if we initialize the bias by 1, then we ensure that we will have the sigmoid open. So the bias is here, basically. Okay, that's fine. And then we need to select the forget gate. So the forget gate is actually self b data. So we want to access the tensor itself. So we'll access the tensor, and then we'll have the hidden size selection out of here, hidden size times 2. So this is this small slice of the forget gate, and we will use the function of fill. And with the PyTorch, as you see that if you want to in-place operations, you can use this small like this underscore at the end, and here we'll set it to ones like that. And let me see if this is working. If it's working, then we can run it. So okay, I will make a screenshot. I believe it's working. So we already finished all of these hacks. This is the next hack. This is a forget gate hack, really good one. So, but also I must say that this is not always appropriate for every problem, especially if you have like short sequences, let's say up to 100 time steps. Maybe even less, then maybe this will be even worse results. So I'm posting the link to the image, and so I will ask the question: is the forget gate hack ready? So let me know. Okay, cool. This is ready. So I'll stop it. So we have the next hack ready. So, and I think we have left only one hack, also a very cool hack. So let me go back to the Jamboard. Not the Jamboard, but to the blog post. So if your model is overfitting, use regularization methods for recurrent networks. So there are specific regularization methods for recurrent networks. Like one is that, of course, between the layers you can have the dropouts. That is the classic method. But I think there is something interesting here. Is I remember zone out was, I think, interesting one. Let me check. So actually there are, and the other one is also was a little bit different, I think. So one is between the layers dropout, but the better option is to add dropouts inside your LSTM cell architecture. So let me quickly check these two papers. So this is from 2016-17. Not sure what, maybe there's something newer after this one. But this is actually very similar equation than it was for the phased LSTM. So let me find it. So here, basically, the z is dropout, and then it's multiplied by 1 minus z to the ht minus 1, and then z times ht. Basically, there's the g, some kind of, I guess, some kind of, I'm not sure exactly where, but basically the idea, this equation is actually very similar to the phased LSTM, but only difference is that the phased LSTM, the z was this phase gate, remember? Phase gate, where it leaves the untouched previous time step, or by some defined phased, lets something in the cell. In this case, this is just a random variable, so this is quite cool idea. Very, very easy to implement. So, and this is one option, and the other option is about the zone out. Zone out. So I think again this was very similar equation. Here again there is a -1 multiplied by this this d. The d is again the random variable, and then we just leave something from t minus 1 or the current t. So I'm not sure really what is big difference between those two papers. Probably the other paper used some kind of G, not sure exactly, like need to look up what exactly, how they calculate the G here for this linear projection. Not sure. Anyway, so we can do this. We can implement the zone out approach probably. So yeah, this will be the last one. So we'll go back to the code and implement the regularization method inside this cell itself. So that's also quite exciting, I think. So let's go back. So add the regularization inside the cell. So we can go to the lines in the cell. So the SOTA LSTM cell, the forward pass, we don't need to learn anything regards to the dropouts, of course. The dropouts are not learnable, right? So they will be here. So we need also some interesting stuff here. So one is that, let's see. So there will be the, as in that paper, DH, torch ones, like, so we will open the gates, basically. Let me think. So we will...
So I opened like how they compare dropout versus the zone out idea. Zone out is that you don't inject randomness by like random variables. You randomly inject previous time steps activation. It's not random, it's from previous time step.
value. Okay. Yeah, that's interesting. So Walters is good at reading papers very fast. That's really good. So he's telling that there is a difference, that there is some randomness injected from previous time steps. So here, let's write with simple dropouts like this. So one thing is that we need to take in account that is it a training or the evaluation. So of course we don't want dropouts to be enabled for the evaluation. So let me check the training. Yes, there is the variable of training. Oh man, sorry, I will go move back. So like this. So except if we want to do the language modeling, where the language modeling, sometimes you want the dropouts to be enabled in the evaluation. So you at least not in evaluation, but in the production. So the outputs would be more natural, more interesting. So TH will be F, the dropout, the torch functional dropout. And here we can use basically, so we can use actually, I think, basically the same thing of this. And the probability of the dropout, let's add as 0.5. And also for this one, DHDC. So we have these two vectors with dropouts, like little gates there. So these little gates we will make inside this equation. So here again, the same way as in the phased LSTM, almost exactly the same way. We can have here as a prim. So we will just call these two as not as C, but the C prim and H prim, because the final C and H will be combination of those dropouts. So here, let's see. So this will be the C is DC multiplied the pairwise multiplication by C prim plus 1 minus DC raised multiplied by previous time step C, and here the same thing just with the H. So we can just replace all of the C's with H. Hopefully now the PyTorch like highlighting will show that I don't have bugs, or will I? Okay, looks good. So, and if I run it, let's see if it works. And if it works, then I will share it. And hopefully then we can just quickly at the last step, I can run this on the Google Colab. And if you add all of the classes, basically it will take a lot of time to train, but you can play out, like do your own ablation study. you can just remove all sorts of the parts of this new code and see the effect of that. So let's see, it's running. Hopefully there will not be errors. This is really interesting, I think. Oh yeah, it works. So it works. I will add this part to the chat, and then we'll wrap up. So this part is also really cool, that we can make these hidden states more resilient to the inputs. So the dropouts and the regularization is the idea that you can avoid situation that it learns exactly precisely those values, and then if something a little bit changes, then it starts doing crazy things. So R dropouts, okay, dropouts, okay, cool. So that's the last step. And now if I shared also that code, now just a second, I will go back. I will set up the Google Colab, and just run a quick run to see that if I don't have some bugs for the GPU. Hopefully not, and then we'll end this session very soon. So sorry for the very beginning that I lost my notes. If I lose my notes, I also can do all of this stuff, but a little bit slower. So, and also more bugs without notes. So if let me share the Jamboard. So the dogs are walking in the top. So here is the Jamboard. I just copied this same code. Here we have the condition that if you have the CUDA, so if I change the runtime to the CUDA, oops. So then we will use all of the code. So this is first thing. The second thing is we can add more classes here, right? 2, 3, 4, and so on, to make this more complex task. Also, we can change the input size. We can change all of these things as well. So if I run it, let's see. Let's just check if there is no major bugs. Oh, the cat is walking with the rows. So top to top. So it's running. Downloading quickly, checking, running. Yeah, there is another thing that we not looked with these workshops, is that, of course, if you have different sequence lengths, then it's a little bit not so nice, because then you need to have the collation, right? Collate function, where you collect that try to have as many similar sequence sizes possible in the batch. And then you need to also have some masks, or yeah, probably masks, stuff like that. So if you have like a natural language modeling task where you have different sequence lengths, it will not be so nice. But it's also possible to apply all of these things, and they should work really good. Okay, so it's working. At least there is no immediate error. It will train really slow, because this is not Torch CUDA and like this CUDA NN library, where they have pre-compiled all of these things with the old approaches. So this is quite new approach. So they have not pre-compiled all of this. And yeah, so that's I think it for today. So I hope you enjoyed at least the second part of our experiments. Next time I will try not to lose notes, and some like session, I think maybe not next one, but one after that, we will have some people from Latvian University also joining and showing some interesting LSTM variants that they do. So if you have any comments, then please let me know, and that's it for today. Bye bye.
Thank you. Bye.